All right, this is the remaining examples from section 2.6. We're looking at absolute value inequalities, and there's two types that we're going to be focusing on. Obviously, we have less than symbols, and then we have greater than symbols. Now, within those two types, there are some places where you'll get some differences or special cases, so we'll talk about that as well. So, looking at this first one, first of all, you have to know what does it mean for something to be a absolute value. Absolute value means that the distance that you're measuring from zero is going to be a positive value. So, like, absolute value of 3 is 3, absolute value of -3 is also 3. Now, when you actually put it in a statement such as an equal sign, and we did that in a pre-video for the section 2.5, so just to remind you about the equations, we had like absolute value of x equals a. We knew that either the inside was a negative a before they took the absolute value, and the other possibility was that x could have been a positive a inside there to get the absolute value of a. So there were two cases. It's a little different when you talk about inequalities. For inequalities, you're saying your distance isn't equal to something, it's less than or greater than something. So for a distance to be, let's just draw a picture of this, less than a. So say our center is whatever the x value is at. So for us here, 0 would be the center. Your center is going to be based off of what would make the inside of your absolute value equal 0. That's the graphical interpretation. So there's two different ways you can get a distance of a. You can go to the right, which is positive a, or you can go to the left, which is negative a. If you want your absolute value to have a distance less than a, that means we're going to be shading the stuff in between 0 and negative a, and 0 and a. So what we end up getting is that this ends up being from negative a to a, okay? And that's kind of what they've written here in the linear inequality. So the way we set up an absolute value that is less than and that it is important that this, you note, is a positive value. We'll have to talk about the special case, which is what if this is a negative value. So if you have absolute value isolated less than a positive value, you set it up by putting the inside or argument of your absolute value in the middle, and you go from negative a to a. And notice it's just less thans all the way across. So the smallest I can get is negative a. In between is what I'm going to be solving for, and then up to positive a. If you have, so let's just write an example of what that would look like with numbers. Let's say if I have x minus 1 is less than 5. Okay, note that this is positive, that's good. And when we go to set this up, we're going to say -5 less than, we put the inside of our argument, and then up to +5. This is how we set it up. We add 1 to all three parts, so that's going to be -4, x, and 6. So this says from -4 to 6 would be our solution. And if you think about it, this one is centered at 1. So that would be what would make this equal 0 inside this absolute value. So to go 5 in either direction from 1, you're going to get a -4 to 6. Now the graphical interpretation, kind of like what I just talked through, imagining it on a number line, that's not so easy if there's a number in front of your x. There's a little bit more going on. But if it's just a 1x, it's very easy to see that this is the correct answer if you draw it out on the number line. What though? This is a special case. What if the number on the other side after you've isolated, so let me show you what I mean by isolating. Let's say my problem was this. First of all, it doesn't look like it's right because it has a greater than symbol. Let's actually do greater than or equal to. But it's not isolated yet. This absolute value is not isolated. So if I go to solve it, I have to divide by -2. And this is the part that actually is the special case. So that flips because I divided by a negative, and this is negative. Okay. If you have an isolated absolute value and you have it less than or equal to a negative number, this is always going to be no solution. Because remember, a absolute value is a positive value. It's going to come out positive whatever you evaluate it to be. So positives cannot be less than negatives. So that's why this case specifically is always no solution. All right, the other situation you could get yourself into is what if you have a greater than symbol? So I have, and again, this is assuming this is positive when we talk about it this way. Give my pen a second to catch up. Okay, so now we're looking at that number line again, and since x is the only thing inside, we're centered at 0, and we have a and negative a on either side. But now we want our distance that we're measuring to be greater than a. So if you're at 0 and you want to be greater than a, you're going to be shading to the right of this a and to the left of the negative a. You want to go out further. So I like to think of the less than case as you're keeping your friends close, they're staying inside your bubble, and the greater than case is you're kind of like putting up a wall around yourself, and everyone needs to be on the outside. So there's two sides they could be on. Now this one is an and case. We didn't state that, but a string is always an and. When you do a greater than problem, so greater, you get an or problem. So you're going to have two different things you have to set up on these. So we have an absolute value isolated on one side by itself, greater than a positive number. Then the two possibilities are you either shade to the left of your negative value. So that's why we write this as x is less than negative a. So the part inside the absolute value less than the negative of this value. Or x is greater than positive a. Okay, so that's the shading to the right. So for example, if I have x, let's say, minus 2 greater than, let's say, 7, okay? I set up my two cases. The inside needs to be less than negative 7, or the inside needs to be greater than positive 7. Notice the positive greater than case is just dropping your absolute value, but the other case, you have to change your symbol and your sign. When we go to solve this, we'll add 2 to both sides. So that's going to be a negative 5, and this one is going to be a positive 9. So when we write that in interval notation, that would be negative infinity to negative 5 parentheses union 9 to infinity, making sure you're in least to greatest order all the way across. So that's how a greater than problem will work out. Now, you could also have, say, a negative on the other side. Doesn't really matter what's inside the absolute value here. If you have an isolated absolute value and you have a greater than symbol, but the right side is a negative number, remember this always comes out positive. A positive will always be greater than a negative. So this is a special case where it's the whole number line or all real numbers. But we'll want you to write it in interval notation. So you'll want to write negative infinity to infinity. You don't really need the reciprocal properties. We put them in the notes just because they're in the textbook. We don't use those in our class. We'll solve inequalities that have denominators in section 2.7. So we do them just by one method instead of trying to teach you a trick and then teach you about what to do for the harder ones. Okay, so we're going to go through and finish up these examples. So this first one, it's isolated. There's nothing around the absolute value on the outside and the front or behind it. And it's a less than and a positive 7 over here. So that's the setup we want to put it in the string. And you do keep both of these as less than or equal to when you're doing the and case. Okay, so that's going to just already be solved since x is by itself in the middle. So that's a really easy one. The answer is just negative 7 to 7 brackets because of the equal to. For this one, we have the absolute value. It doesn't matter what's inside here, but the absolute value is isolated. We have a greater than and a positive number on the other side. So that's the perfect setup for the greater than case. So we do less than the negative of that number or greater than the positive of the number. Now, because there's a negative inside here, when we go to solve this, it's actually going to flip which one's the greater than and which one's the less than. So we divide by negative 1 on both sides. That's going to make that less than negative 2. So when you write your interval notation, be careful not to just read it from left to right. You want to write the smaller one first. So that's negative infinity up to negative 2, no bracket because it doesn't have an equal to, union with 2 to infinity. Okay, let's look at C. So we need to take C and isolate first. You can't solve until you've isolated. So we're going to add the 0.3 over to the other side. That's going to make that 0.4. Then this is a absolute value less than and a positive number. So we set it up where the x minus 3 is in the middle of the string. We're going to add 3 to all the sides. And I'm writing it here so you can see we're lining up our decimal points. So the 3 has a decimal point at the end of it. So this would be 2.6 and x and 3.4. So in interval notation, that's 2.6 to 3.4, parentheses on both. All right, let's look at D. This one has a little bit more to do to isolate. We're going to add 2 over first. Be careful that your absolute value symbols stay separated from your numbers. Sometimes they start looking like ones. So that's going to be a 12. We're going to divide both sides by 2. That's greater than 6. Okay, it's a greater than case and a positive number over here, and this is isolated. So we set up 2 cases. Remember, it's the OR problem. So, oops, I didn't need an X on that guy. So negative 11 minus 7x is less than the negative case. That's to shade. That sets it up so you're planning to shade to the left. Or negative 11 minus 7x is greater than positive 6. So you're planning to shade to the right, to positive infinity. But when we go to solve this one, again, we're going to end up dividing by a negative. So it's going to flip-flop which one is which. That gives me a 5 on that one. And then I divide by negative 7. So that becomes greater than negative 7/5. Or sorry, backwards. 5/7. Talking and writing doesn't always work. Okay. So yeah, we're dividing the 7 over, not the 5. Excuse me. On this one, we're going to add the 11 over. So it's going to be 17. And again, dividing by negative 7. So that's going to flip that to a less than. So negative 17 over 7. Make sure you write the less than case first. So this will be negative infinity to negative 17 sevenths. We don't turn these into decimals. Union with negative 5/7 to positive infinity. Okay, I think we're on our last one. Absolute value is isolated, less than symbol, but this is negative. Remember, this always comes out positive, so a positive can never be less than a negative, which means this one is no solution. There should be no solving when you've isolated it and the other side is negative. Now, you have to be careful. Sometimes you'll have stuff like this, and when you go to isolate it, it turns into a positive. So just be aware that you can't determine if it's a no solution until you've isolated. So always isolate first before determining if it's no solution or the all real numbers case, because this one can be solved. If you try to solve this, you will get answers, but they do not work in the actual problem. So that's why we need you to recognize the no solution and the all real number cases. All right, that'll be it for this video.